An object moves in a straight line if the net force on it acts along the direction of motion, or the net force is zero. However, if the net force acts at an angle to the direction of motion at any moment, then the object moves in a curved path. An example of this is projectile motion, which we discussed in the previous video. When the direction of the net force acting on the object is perpendicular to the direction of motion at all times, the object moves in a circular path. In this video, we'll be studying the circular motion of objects and how Newton's laws apply to this type of motion. Consider an object moving in a circular path about a fixed point O as the center. Let's assume that the object moves from point A to B in the time interval between 0 at a point A and t at point B. In this interval, the object rotates through an angle theta. This angle theta is referred to as the angular displacement of the object and is conventionally measured in the anticlockwise direction and expressed in radians. The angular velocity of the motion, omega, is defined as the rate of change of angular displacement with respect to time. Mathematically, we can write that as omega equals d theta dt. We can find the relationship between the angular speed and the linear speed of the object. Since we know that speed is the rate of change of distance with respect to time, we can say that the speed is the rate of change of arc length AB with respect to time. And our arc length AB is given as r times theta, where r is the radius of the circle or the circular path through which the object moves. We can then write V as dr theta dt, which we can further write as r d theta dt. Now, if t is sufficiently small, we can write V as r d theta dt. And recall that our angular velocity, omega, is defined as d theta dt. Thus, we can write V as r times omega, or V equals omega r. The angular acceleration, alpha, can be defined as the rate of change of angular velocity with respect to time. Mathematically, this can be expressed as alpha equals d omega dt. If angular acceleration is constant, we can write our equations of motion for circular motion, similar to the equations for rectilinear motion as follows. Omega equals omega naught plus alpha t. Theta minus theta naught equals omega naught times t plus half alpha t square. And finally, omega square equals omega naught square plus 2 alpha into theta minus theta naught, where theta minus theta naught represents the angular displacement within the time elapsed. We're now going to prove that an object moving in a circular path must have an acceleration perpendicular to its direction of motion, and we are going to find the magnitude of this acceleration. For this, we consider the uniform circular motion of an object about a center O. An object which moves in a circular path at constant speed v is said to experience uniform circular motion. It is important to note that while the speed of the object remains constant, its velocity does not. Its magnitude remains the same value as the speed, but its direction changes continuously throughout the motion. Thus, an object revolving in a circle is continuously accelerating, even when the speed remains constant. To investigate this acceleration quantitatively, we consider a short-time interval, dt, during which the object rotates through an angle, d theta. v1 and v2 are the velocities at points A and B respectively and are tangential to the circular path. Because v1 and v2 are both tangents, the angle between them is also d theta. During the time interval dt, the particle moves from point A to B, covering a distance dl along the arc, which subtends an angle d theta. The change in velocity is given by v2 minus v1 and is written as dv. This can also be rewritten as v2 equals dv plus v1. Our acceleration is defined as the limit of delta v divided by delta t as delta t approaches 0. If we evaluate the limit and let delta t be very small, approaching 0, delta theta will also approach 0, and this will make v1 almost parallel to v2, and dv, the change in velocity, will be essentially perpendicular to both velocity vectors, thus pointing towards the center of the circle. Since the acceleration is in the same direction as delta v, then the acceleration too must point towards the center of the circle. This acceleration is called centripetal acceleration because it points towards the center of the circle. Now that we have determined the direction, next we find the magnitude of the centripetal acceleration. We can observe that both triangles are geometrically similar. If we take del theta to be very small and set v to be equal to v1 and v2, because the magnitude of the velocities is assumed not to change, we can write delta v divided by v equals ab over r. We can also observe that the chord AB is almost equal in length to the arc length delta L. Thus, we can write that delta V over V is approximately equal to delta L over R. This becomes an exact equality when delta T approaches 0, because then the arc length d delta L equals the chord length AB. We want to find the instantaneous acceleration, so we let delta T approach 0. And we can write the above expression as an equality and solve for delta V. So we write delta V over V equals delta L over R. And solving for V gives us delta V equals V times delta L over R. This is the magnitude of the change in velocity vector, delta V. To get the magnitude of the centripetal acceleration, we divide delta V by dt and find the limit as delta t tends to 0. Now what we have here is that the centripetal acceleration equals v over r times dl dt, where L is our arc length. But we know that dl dt is equal to the speed of the object moving in the circular path. So we can write our centripetal acceleration as AR equals v squared over r. This is the magnitude of the centripetal acceleration, and this equation is valid at any instant in circular motion, even when v is not constant. So this means that this equation for centripetal acceleration can be applied to non-uniform circular motion as well as uniform circular motion.